Hi, my name is Min.
My name is Prasun.
And I'm Arham.
And we are team number 1071 from Wabash College. And we attempted to model and solve problem A titled, It is Raining Space Dust.
Our presentation will follow a four-part story. First, we'll establish the theoretical model, which is the heart of the challenge. Second, we'll validate the model with a sanity check. Third, we'll show you the results of our numerical simulations. And finally, we'll show you how this all leads to a complete solution to the problem. Our solution therefore requires 3 steps. First, we must build a rigorous mathematical model of this entry process. Second, we run simulations to map the transformation. And third, we use this map to work backward and recover the original distribution.
So let's begin with the first and most important step, which is the theoretical model. As this is a differential equations competition, the model is the foundation. So we modeled a system of 8 coupled first-order differential equations that describes the state of the particle at any given time. The system is composed of 4 parts. First, kinematics. This is a full 3D model, so we will have 3 ODEs for position and 3 for velocity. The derivative of position is simply, obviously, velocity. Second, dynamics. This is where the physics begins. So the next 3 ODEs describe the change in velocity or acceleration, which comes from Newton's second law. The total acceleration on the particle is a vector sum of 2 main forces. The first is gravity, which is a central force pulling the particle towards the center of the Earth. The second and more dominant force is aerodynamic drag, which is a more complex force that opposes the velocity vector and is a function of altitude, velocity, and the particle's changing radius. Third, the energy balance. This is the 7th and most important ODE, and it's a thermodynamics model for the particle's temperature. And this comes from the first law of thermodynamics, which states that the rate of the change of the particle's internal energy is equal to the energy it gains minus the energy it loses. The energy gain is convective heating from slamming into air molecules, and this term is proportional to the density of the air and the cube of the velocity. The energy loss has 2 terms. Firstly, radioactive cooling, which is the heat the particle radiates away proportional to T to the 4th, and ablation energy, which is the energy that is lost to vaporization. So this brings us to the final equation, ablation, which describes the change in mass. This is the switch that couples the entire system. So as long as the particle's temperature is below its melting point, mass change is 0. But the instant temperature exceeds the melting temperature, this differential equation kind of turns on. And the mass loss is now driven by the net heating, and this change in mass then feeds back into the drag force and the energy balance.
To make that drag force term accurate, we cannot use a simple constant drag coefficient. The physics of a particle moving at 40 kilometers per second is very different from one moving at 10 meters per second.
Therefore, we use a continuous drag coefficient function that is dependent on the Reynolds number. As you see in the plot here, our model correctly bridges 2 regimes, right? At high Reynolds numbers, it is in the Newtonian regime with a low constant drag, but as the particle slows down, it enters the low Reynolds number Stokes regime, which drag becomes much and much higher. This is an important observation for modeling the final deceleration and stopping of the particle. So we have a rigorous model, but is it correct? We'll now move to part 2 of model validation.
This plot is our sanity check for the entire model. It justifies the ablation physics. The blue line is the convective heating, and the red line is the radioactive cooling. We've plotted this for a typical particle in the main ablation zone. The story here is simple and powerful. We've marked the melting temperature of silicate rock at 1650 Kelvin. At this temperature, look at the difference between the lines. The incoming heating from the blue line is orders of magnitude higher than the energy the particle can radiate away from the red line. This enormous surplus of energy, this heating gap, must go somewhere. It goes directly into vaporization. This graph proves from first principles that ablation is necessary. The model is therefore pretty sound. Now I'll pass it to Arham to show you the results of this model in action.
With our model built and validated, we move to simulation results. This is our results dashboard. We run 5 diverse scenarios to test the full range of the model's behavior. The 3D plot at the top left shows the trajectories in space. The slide view shows the path shape and downrange distances. The altitude versus time plot shows how quickly they decelerate. And the summary table, which we'll analyze next, tells us the final physical state of each particle. You can see we tested 5 distinct cases: an unmelted survivor, a cosmic spherule, a particle we thought would be fully ablated, a shallow entry, and a vertical entry. This gives us a full picture of the model's behavior. Let us dig into the data. First, the side view plot clearly shows that our model correctly captured the entire angle. The 90-degree vertical particle in orange travels 0 kilometers downrange, as it must. In contrast, the 30-degree shallow particle in blue travels almost 70 kilometers horizontally. The path shapes are physically correct.
Second, in the 3D plot, that abrupt turn you see isn't actually a turn. That's the particle hitting the dense atmosphere at around 100 kilometers altitude. This is the moment its high velocity coasting phase ends and its rapid deacceleration and ablation phase begins. Finally, based on the simulation data, our model correctly classifies the outcomes we see. Unmelted survivors that kept 100% of their mass and cosmic spherules that lost significant mass from melting.
And this is where the most interesting non-obvious physics appears. Let's look at the red particle, which is our cosmic spherule. It starts at 500 microns, but it was so large and had so much momentum that it plunged deep, heated intensely, and lost 97% of its mass. It survived only as 158 micron droplets. But even more interesting is the purple particle. We expected our fast 40 km per second particle to be completely vaporized, but the model found that it survives. And why? Well, the model found that its rapid ablation and radiation shed energy so fast that it was able to cool down and stabilize as a 78 micron spherule.
So our model works, it's powerful. Now we can use it to build the final solution.
The dashboard showed 5 runs. We can now run this 10,000 times or more, varying this initial radius and initial velocity. The result is these 3D surfaces, which we call the transfer map or K matrix. This map is the atmospheric filter. The color here shows the final radius for any given initial radius and initial velocity. You can clearly see the survival cliff where large, fast particles are completely destroyed and their final radius drops to 0. And this map is the final key. As this diagram shows, the problem is to find the initial distribution x. We're given the final distribution y from the strata data. We have just simulated the transfer map k. This gives us the metric equation k times x equals y. We can now use a non-negative least square solvers to find x. This provides the complete direct answer to a SCUDEM prompt.
Thank you, Arham. I'll now briefly conclude. To summarize, we successfully built a continuous energy balance model for cosmic dust entry. Validating its physics, our simulations produced a rich set of outcomes, including survivors, spherules, and ablated particles, and even captured complex, non-obvious behavior. This simulation engine generates the transfer map K, which provides a complete and direct solution to the SCUDEM inverse problem. Thank you.